Hello, everybody. All right, thanks for coming out. I'm David Richardson. I'm a developer at Susquehanna. In a previous life, I was a computer algebra researcher, and I'm going to be going through some stuff that I did for computer algebra. So we're going to run through a problem that people actually care to optimize. We're going to look at some hand-tuned assembly that had been what people have been using, and then we're going to do something faster than assembly. This is kind of a good story of how all optimization goes. This is maybe a bit of a more extreme case. So we took 4 lines of C++ code and turned it into about 85,000 lines of C++ code. But along the way, for the 18 months or so it took us to figure out how to do it, we also set 3 world records. So it's a little bit more extreme than usual. You're usually not going to spend that much time on things, but there's a lot in here that's just sort of general optimization. So first, a little bit of background. So everybody has sort of the normal arithmetic you use in computers. So this is just some word that's completely full. So it's the maximum value that it can hold. And let's say you come along and you want to add something to it. So the normal outcome here is you just overflow. And hopefully the application deals with it somehow, but that's it. There's no more memory. You're done. So in multi-precision, you start in the same spot, and instead what happens is you come to add, and you just allocate more memory. And you say, OK, now I need a bigger number. I'll take some more memory. I'll allocate it. So any problem that's doing this, it gets sort of 2 unique properties out of these. First, you become obsessed about how many times you've added things together, because you need to know how long the operand gets. That's going to the cost of doing arithmetic now is not fixed anymore. It actually depends on the length of the inputs. And it really always did, but because in a normal computer, it says I'm capping you at something like 32 or 64 bits, you can pretend it's constant time. So that all of a sudden is going to change how you have to think about the performance. Also, it means that anything like this is going to use an incredibly large amount of memory. So if you've ever wondered what are Maple and Mathematica doing with all of the memory when you run them, what they're doing is this. They're allocating lots and lots of these. People variously call them words or beta digits or limbs, but basically they're just the unit of computation as you add more memory to a longer number. So what do these things get used for? They're an incredibly core primitive of computer algebra. So when you're using something like Maple or Mathematica, all the answers they give you back are exact. There's no rounding. And we also like to joke that all that memory is the price of exactness, because if you didn't have it, you couldn't do the exact computation. It gets used a lot in cryptography. So something like you want to generate a public key and a private key, and you need really big numbers so that you can factor them. So clearly, if you're generating something like a 2048-bit key, you're not fitting it into a 32-bit word. You need a library like this on top of it. It also gets used some in computational geometry. There, it's maybe a little bit less obvious. So a lot of times you want to ask questions in computational geometry like, do these 2 curves intersect with each other? And then you're going to do something on the basis of it, of maybe render something or conclude that one thing is inside of another thing. You don't actually want the error there. So if you actually want to be able to say, do they really intersect, you need the precision. And then there's more humorous applications of things like, if you've ever seen one of the contests for who can compute more digits of pi, they needed multi-precision too, because otherwise, how could they get all the digits? So it actually makes a pretty big difference in the speed and the memory consumption that you're going to have. And there's also another thing. It makes a big difference for algorithm crossover points, which we'll get to in a little bit. So how do people actually implement this? So what they actually do is usually use a library called GMP, which stands for GNU Multi-Precision. And this is from GMP's website. And I bolded the text that's being highlighted. So they're basically the only reason that they exist is to be fast. That's their big claim. They say that they're as fast as possible. And they make 2 kind of important parts of that claim. They're fast if the operands are small, and they're fast if they're big. So they're basically saying they're good at everything. And then they go on to kind of talk a little bit about why. And one of their main things that they're getting their speed from is hand-tuned assembly. So that's kind of, they've set themselves up as we're fast, and we're fast because we pay attention to computer architecture, and we write in assembly. And they mean it. Basically, it's almost all in assembly. If you go and look, there's more ASM files than there are C files, and there's way more lines of code in the assembly than there is in anything in C. So one of the things about them, and why they're used so much, is that their performance claims are actually true. Lots of people say, I'm fast and I'm really good at things, and then you try it and it doesn't quite work out. In their case, most people conclude, well, I'd rather use them. They're much faster than anything I'm going to do. They're fairly actively maintained. So as CPUs come out, they adapt to them. And it's dual licensed under 2 GPL licenses. They're trying to be reasonably accommodating and let you use it in a wide range of things. But they also want it to be open source. It is, after all, the GNU multi-precision library. So it's not something like open source where it's good enough to be open source but not good enough to be free software. So they're basically the gold standard for multi-precision, especially on Unix. The known to work on Windows is their quote, not mine. Basically what they mean by that is they don't care. And the reason is that there's not a lot of scientific computing on Windows, so they're not really giving up very much market share. So who's using it? There's some examples. So Maple and Mathematica are kind of the flagship computer algebra platforms that people are likely to have seen and used for something. Sage is an up-and-coming one that it's basically gluing together with Python a whole bunch of open source computer algebra pieces. They're trying to replace Maple and Mathematica, and they're having sort of mixed success depending on what it is that you actually want to be able to use from them. They actually also asked if they could incorporate some of the stuff that I'll be talking about. The Magma is a bit of a more specific one. It's a computer algebra library that a lot of people use, but it's not sort of end user facing, so it's another fairly common one. It's also sort of interesting because the developers of Magma own a lot of sheep, and so you get to hear a lot about wool prices when you're talking to them. So the GNU compiler collection is another one. If you've ever tried to build GCC from scratch, it's going to want GMP. And it's using it for languages that have infinite precision as part of the language, and also people that use it as libraries. And it's also in things like the Glasgow-Haskell compiler. So this is just kind of a smattering of uses, but it's very widely used. It's actually very easy to use, and it's well documented. It has bindings in a lot of different languages. There's a lot of good things to say about it, and it's definitely deserved wide use. So what do they mean by optimized? So I took this out of a comment that is in that file in the latest distribution of GMP. And so a little bit about sometimes what they do to get the assembly. So they don't actually want to write all of the assembly by hand. They just want to make sure that it's good and it's stable. So a lot of times what they'll do is they'll write in C and they'll compile it, but they'll compile it to assembly and save it, and then take a look at it. And they'll decide, well, maybe I'm willing to keep the assembly, or maybe I think it could be better. And the reason they're not just using the compiler is because they want it to be stable. Once they've locked it in and said, this is the performance we want, they don't want the next compiler version to do something different. So the part that I bolded is that they're not too happy completely with the compiler performance because it's 3 cycles slower than theoretically possible of a total of 22 cycles. The per lim notation in GMP, that is the machine word. So on a 64-bit computer, it's going to be a 64-bit integer that they are allocating to generate the digits of the multi-precision. So they also are complaining about, for some special cases, so the compiler, for whatever reason, decided that the loop that they had, when it was short and it was only going to be 1 to 3 iterations, it was going to generate special code for it. And so they've looked through, they've decided, okay, this is bad, it's not going to get peak performance, it's going to be something like 10 to 15% off of what it could have gotten. And then they have a comment that says, really, someone, when they get a chance, should come back and handwrite this code the way that they have in, say, other things they've optimized. And then they give an example of one. So these are some other comments that I grabbed out of this one. This is the one that they're saying is how you're supposed to do it. And so they start out and they say, let's list all the kinds of instructions that we're actually using in here. And so basically any CPU that you get, there's some architecture manual that ships with it, and you can just go get it. And it'll tell you, these are all the different kinds of units that are in it that perform logic, and it'll tell you This is how many there are of each of them, and it'll tell you these are the kinds of instructions that are processed in each one. So they went through and they got it, and they added them up. And the meaning of these, you'd have to go look at the document for the CPU you were using. But generally, they're going to be things like, so the first one is, I think, floating point multiply. The next one's floating point add. The next one's a memory load. The I shift is an integer shift. And then so on and so forth. And they get it down to the end, and they say, there's 55 instructions that are in here. And then they have to point out that there's a move that could get optimized out, but they actually had to write it in there. So they then go and try and run it and say what happens when they did it. So they've added up exactly what should happen. And the loop executes in all 56 instructions in 14 cycles. And in case you don't have memorized what that means on an UltraSpark, they then go on to explain that 14 cycles is the sustained peak execution rate of 4 instructions per cycle. So basically, the manual for the CPU told them that when you have all the pipelines completely loaded and when it is finishing instructions at peak speed, that it can finish 4 of them. And this is actually the goal for any CPU-bound problem. You're on some processor, it's capable of doing a certain number of operations per cycle, and you're never going to go any faster than doing all of them that it can possibly do. So another way to think of it is there's parallelism in the processor, and if you hit this, you took all of it. You're using every single bit of parallelism that's available. So this one, they're really saying is optimal. There's no 10 or 15% off. There's nothing more to get here. You have, with this algorithm. Now, you might later decide I want a different algorithm, but in terms of how they've implemented it, it is peak execution that you're able to get. And there's also the occasional, you can say, well, it's peak execution, but of things that didn't need to happen. So assuming that they went through and took out any extraneous operations that weren't actually relevant to what they're doing, which they did because that's the kind of stuff they worry about, this is it. This is as good as you're going to do. So maybe another question of what is the algorithm? So they're doing these basic arithmetic things, and they're doing all integer arithmetic. And so the first odd thing you notice is they're using 8 floating point multiplies per limb. And so they then go on to explain how they break it up into a bunch of little pieces, and the details aren't too important. But one thing you notice that's a little bit odd as they're moving through is, so they're trying to do 64-bit arithmetic here as integers, and they are flipping back and forth between, at some points it's 16 bits, at some points it's 32, other times it's 48-bit partial products, and then sometimes they have 49-bit terms that they're using. So does anyone have any guess for why they're doing that? There's only 4 integer execution units on this CPU, and they know that there's more floating point. So what they're doing is they're going through and saying, if I do all of the work to take these things that are integers, convert them into floating point numbers such that I control the rounding error, and I know that when I take it back, I've made no mistake, and it's just the same as having been an integer operation, let's go do that because we're able to do more of them. They're also taking advantage of a bit of a trend that, in general, more people care about flops than they do about integer operations. And that's going to be kind of true on most CPUs. So one thing you need to figure out when you're optimizing is, are you actually the problem that your architecture is tuned for? And in their case, the answer is no. And so what they're saying is they put tons more silicon space, tons more engineering effort on the chip into making floating point work quickly. Can I turn my problem into something they've optimized heavily and then take advantage of all that extra chip real estate and then come back to the actual answer they want at the end? So there's a question at this point of, look, realistically, what are you going to do to beat that, right? So they know the hardware. They're very well studied. They know all of the best published algorithms in this domain. There's also a lot of algorithms that they invented. There's an especially neat one in there. So on the UltraSpark, when you're adding those numbers up, as you go across the digits, if there's a carry, you need to somehow take that forward and carry it into the next digit and do the arithmetic. A lot of people give up a bit to save space to copy the carry forward a digit. They don't give the bit up because they know how to reconstruct the carry. For anyone with an EE background, it's a little bit similar to how things like a carry look-ahead adder works as opposed to something like a ripple adder. So They've also been at this for a long time. They started in 1991. I think there were actually some releases of bits and pieces of it that were around before that, but they've been doing it for a long time, and they think they're between 10 and 20% from optimal. So maybe there's a weakness, right? They're general. They're good for large and small inputs, so maybe they gave something up there. And so here's where we get to crossover points as an optimization technique. So frequently there's multiple algorithms that do the same thing. So say you want to sort something, you've got bubble sort and quick sort. So each one of them has different time complexities, but in real life the constants matter. And so it might actually be the case that the higher time complexity algorithm for a small input is going to actually be quicker. So one common optimization you try is you say, okay, if that's true and there's a bunch of different algorithms that do the same thing with different complexities, let me figure out on my hardware for my implementation what size input is best for each type of algorithm. So here's an example, and I picked this because it's a bit of a Philadelphia story because it ends with someone at Penn having the world record for it. So let's take integer multiplication. So we start with the classical multiplication. So this is basically if you had a piece of paper and a pencil, how you would actually multiply two numbers, and pretty much how you learn in high school or elementary school or whatever you've learned it at. And that's n squared in the length of the operands. So in the 60s, someone came along and developed something that's a little bit better than that. And whenever you see crazy powers like that, where it's a couple decimal places, what it really means is it's probably some complicated divide and conquer algorithm. And instead of writing out all of the terms that you actually got, I just sort of computed the first 3 digits. No one actually wants to see term after term of what's been written out. So then by the late 60s, people have gotten a little bit better. And then by the 70s, someone came along, and now we've dropped down to we have an n log n and then a log log n for the last term. And GMP actually uses this, or at least it did the last time I checked, for decimal digits that are between 33 and 150,000 digits long. So you get a feel for this that you actually need a pretty big input before this starts kicking in. So, and then the last one was developed in 2007, and this is actually a roughly normal time trajectory for these, of that there were sort of early gains made in the 60s, and then within the last 10 years or so, people kind of finished it out. And now you have an even more complicated time complexity function. It still has the n log n in the beginning, and now it's dropped down to 2 raised to the order of an iterated logarithm. So there's an interesting tension if you go to a computer algebra conference about things like this. So there's people like me that do implementation and optimization, and there's people that make algorithms, and in general, they're not the same people. And the people that make the faster algorithms always say, why don't you go optimize my complicated algorithm? If we work together, we'd have the better algorithm and the better implementation, and then clearly that would be better. But there's a little bit of a hint in a complexity function that is that complicated about why, in fact, it's typically 2 different people. And the issue is that the algorithm, if it was that complicated to write down its complexity, think about how complicated it is to actually implement it. It's an incredibly complicated algorithm, and the odds that you could get it right implementing it in a first pass is low. Actually, what you do when you implement them is you implement the classical algorithm first because you're positive you did it right by inspection, and then you implement the other very complicated algorithm and typically spend weeks or months trying to get it to match the classical implementation for all of the inputs that you care about. And that's just to get it right, never mind to get it fast. So GMP is good at crossover. They didn't leave very much on the table. They do a link check, they jump. We're not going to beat them here. And this is kind of the first part that will come up in any optimization process of you have an idea, you try it, it turns out it doesn't really work. So do you give up or do you keep trying? So maybe if we step back a little bit and we say, well, what problem are they solving? So they only do a single multi-precision arithmetic operation at a time, and they do it for 2 operands. So you can add 2 numbers, you can multiply 2 numbers, you can subtract them, but if you want to compose them and do any kind of pattern, you have to do the composition. And they're quite good at just doing two operands. This is the thing that they've heavily, heavily optimized. So now, what do people do with GMP? So it's almost never the case that your problem is, I want to add two numbers and know what the answer is, and that's the extent of the calculation. So you're going to implement algorithms, and they're going to perform lots of arithmetic operations to solve some other problem that you actually care about. And so when you're tuning it, you don't care how long it took on any individual operation. You care how long it takes to finish the entire computation that you care about the answer for. So maybe this is an opening that what if we try and optimize an algorithm and one that's able to use single arithmetic operations as primitives, but that gives some result that's more important than just a single operation by itself. So the problem we worked on is root isolation. And there's lots and lots of math we could talk about, but don't worry, we're not actually going to talk about it. I just have a couple schematics of it. So you have some input polynomial, and what we want to do is get a set of isolating intervals. So here is our schematic polynomial, and we want to know where it crosses the 0 line. And we don't want to actually find the root. We just want to figure out that we have some interval that there's only one root inside of. And you could want to do this for a couple of different reasons. One is you might just want to know something like how many roots it has. Another one is you might just be trying to locate roughly where it is so that then you can use a numeric method. And a lot of them don't behave very well when there's multiple roots near to each other. And so this is guaranteeing, no, there's only one. It's a fairly common operation in science and in computer algebra. So it's actually important enough to be worth optimizing. There's a bunch of stuff that uses it. If we had picked a problem that no one really cared about, we wouldn't have spent 18 months on it. The other thing about the polynomials is that we're isolating on, their coefficients are exact integers. And so because their coefficients are exact integers, we're going to get a ton of these operations that GMP is good at when we're going through to do it. So what people typically do is they use GMP to implement it. So the method that I was working on is called the Descartes method for real root isolation. So nothing about complex roots, only real roots. And at a high level, what it does is it transforms the polynomial and maps all of its roots to the interval 0 to 1. And that's represented as a tree. And it then proceeds by just bisecting intervals, looking for roots. So the first thing that happens is, I don't know if everybody can see the gray. So the interior nodes are all gray. And the interior nodes have many roots in them. So we haven't finished yet and computed the isolation. And as we keep bisecting, we're going to get these leaf nodes. And the leaf nodes all have exactly one root. So now we're done. This is the goal of what we're doing. And I left off the roots that would be here off of the edges that have nothing in them, which is just sort of a standard way of representing it graphically. So when we're processing this recursion tree and going through, the nodes require 3 Taylor shifts or 1 de Custódio algorithm. And it doesn't really matter what they are in the context of this talk. It just matters that they're basically all of the computing cost of doing this. And so people typically implement this in GMP. So we've got 2 choices right now. We can say, OK, let's try and use the structure of the computation to reduce the number of arithmetic operations. So it worked for multiplication. And basically, it works for everything, where you try and come up with some better time complexity. So maybe we could do that. But our other choice is we can just reduce the cost of the arithmetic operations. And so that's basically has worked for GMP. So those are sort of the 2 choices we have available. So what about reduce the number of operations? So this is an algorithm problem. I'm a systems person. So are all of my collaborators. So it might be possible, but we were not going to make any progress here. And not only, so the slide says I didn't know the lower bound. It was at the time somewhat debated what the lower bound was. So it's a complicated enough problem. It wasn't even clear what optimal was if you were working on it. So how about reducing the cost of each operation? So this is an implementation problem. This one seems much more likely that we'd be able to work it out. So what does it cost when you're doing the GMP arithmetic? So there's two parts. There's memory access to get at the words, and then there's arithmetic on the words once you have them. And GMP does not reuse a word across multiple operations. So it takes a pair of operands, it does the operation on it, it loads all the memory, it uses it once, and then it's done with it. If it needs it again, it loads it again. So compilers are incredibly unlikely to figure out how to reuse any operations that happen to occur when you're calling multiple GMP calls. And the main reason is actually what GMP did. So the fact that they made sure to actually saturate the CPU means that there are no little spots for the compiler to stick an extra operation into. And it also means that they have put a ton of instructions all right next to each other. So compilers, when they're optimizing things and scheduling, are not able to look at the entire program at one time and say, let me look at every instruction that's in here and reorder all of them together. And the reason they can't do it is because it would take too long. You would start having multi-day compiles for relatively trivial programs if they did that aggressive level of optimization. So they basically look at a small window of instructions and they optimize as much as they can see and get done reasonably quickly. So GMP has basically made it so the compiler has no chance to help them, which is fine. They've gotten a lot of benefit from it, but it takes away that one avenue of optimization. And so another question is, we've got two things we can try and optimize here, right? We've got the arithmetic and we've got the memory. So memory access is much more expensive than arithmetic. And that's pretty much going to be true on any CPU that you're going to get to use. And it's especially true on an x86. So roughly, an integer operation is about 1/3 of a nanosecond. You can kind of back that out of the clock speed of the chips these days. But a cache miss is about 100 nanoseconds. So you clearly have a chance to try and get a much bigger benefit out of getting rid of a memory operation than you do out of getting rid of a single arithmetic operation. So what we ended up doing doesn't actually really reduce the number of arithmetic operations, and actually it increases them a little bit. We do a couple extra ones, which we'll see in a few slides. But we're going to try and reduce the number of memory accesses that actually happen. And so this effectively reduces the cost of the arithmetic, because right now, the way things are implemented, doing the arithmetic is bundled with the memory operation. So the other thing that this also kind of brings up is, so typically you have a textbook. It has some ideal description of a machine, and it counts operations. And that's the complexity of the algorithm. And everything gets counted more or less the same. Of, oh, an add is the same as a minus, is the same as a memory load, is the same as a memory store. That's not true in real life. So we're starting to try and get a more accurate view of what's going on to try and optimize what exists, instead of using a model that, while gets you pretty far, doesn't help you with this problem. So there's a memory trade-off. And so there's some fixed budget when you're getting memory. And typically your constraints are how much money you're willing to spend on the server that you're buying, and how much power it's able to draw, and also how much area on the chip you're willing to take up. And these are the three dominant constraints. So given these budget factors, you have two choices. You can have fast memory or you can have high capacity memory, but you can't have all of it. And so you're just kind of stuck with it. There's going to be some slow memory and there's going to be some big memory. So what does this look like on x86? So you start and you have the fastest, most expensive memory, which is registers. So these are basically right on the CPU. Whenever you see something like Intel says, look, here's the peak bandwidth that you can get off of this chip when you're moving stuff around, they basically mean if you're copying things to and from registers, look how fast it goes, and it all goes down from there. And that's also why, in general, when you try and do it yourself or write your own application, you don't get the high numbers that they list on the spec sheet. So the next thing you start having is cache. So you've got cache that's associated with a specific CPU core, and that's going to be fastest for that CPU, but a little bit slower than the registers. Now you start having cache that's per socket. So this is the stuff that's shared across CPUs that are packaged on the same die. And then we get to memory. And there we also have the same pattern repeat again. So there's local memory that's directly connected to the same NUMA node that a CPU is plugged into. And that's the fastest you can get to it. And then there's all the other memory in the system that has to do things like go over the QPI link, and those are in the remote nodes, and they all start slowing down. And let's say you run out of memory, now you've got to go to the hard drive, and it repeats again inside of thereof. Hard drives have their own tiers of caching inside for the same reason. So in general, you want to try and stay as far up this list as possible if you're trying to optimize something. So lots of people know memory access is expensive. It's pretty hard to not notice if you're doing any kind of performance tuning that the memory matters really a lot. And so there's an obvious idea, right? Once you load something, you want to do as many computations on it as possible. So for a regularly structured problem, this is called tiling. And it's because you tend to draw a lot of little pictures that you're trying to fit over the computation, and they look kind of like tiles. So there's another thing when you're optimizing that you don't actually really want to look at a specific algorithm if you can avoid it. And there's two reasons. One is that the detail of a given algorithm is going to obscure what you actually need to do in terms of the machine, because you're thinking about two things at one time. You're thinking about what is the machine doing and what are the requirements of this algorithm. And it also makes it really hard to reuse, because if you tangle yourself up with the algorithm you're optimizing, anything you come up with is not going to work for a different algorithm. It's only going to work for that algorithm. So what you're actually really optimizing from the machine perspective is a dependency graph. And some of the nodes might have different costs, but basically you're just trying to schedule the graph and handle all the dependencies. And there's another upshot of this. So if you formulate it this way, instead of looking at more math for root isolation, now we get to just look at graphs. And there's also a key advantage here of that I personally don't understand most of this math, but I also did most of the optimization. So by breaking it up like this and having this abstraction in between, you let people with different specialties work on the problem together. So these are now back to the major sub-algorithms that I was talking about before when I had the recursion tree. And it doesn't really matter how these work. It's just that represented as a triangle, you have a whole bunch of inputs that come in along this edge, and you have a bunch of inputs that come here. And the way you process them is you take the two inputs to this node and you sum them. And then when this one's done, it becomes the input to this one and the input to this one. And you continue that pattern all the way through, and eventually you get out on this edge the answer. And so this is the one that you had to do 3 of per node. The algorithm where you only had to do 1 of them is almost the exact same thing, but now in the triangle, the inputs come in on this edge, and what happens is to evaluate this node, you take the one below it as an input and the one to the other side of it and add, and now you get the answers out here. And intuitively, the fact that you get 2 answers out of one invocation of this and you only get 1 out of this one is why you can do 1 of these and have to do 3 of those. So if you start tiling for multi-precision, the first thing that you see is, OK, we can break the triangle up into regions and start trying to handle 1 of them at a time. And if you remember back to the first picture where when we were adding things together, we had to keep allocating extra memory as they got longer. The analog for tiles is that you have a stack of them. So this is basically the beginning of the number. This is the next part of the number, the part after, and it just keeps going until you have enough of them to make up the entire number. So you get this pattern where you have these tiles to deal with at the beginning, and then you can kind of think of them as coming out of the board and just keep doing them over and over again until you're done. So how are we going to pair these? And so this is saying, let's say this is the degree of the polynomial plus 1 extra one, because if you look back at the picture, you need that many inputs. And so if you had 11, you'd get a triangle like this. And so you can see that there's a couple of patterns. So the easy one is squares, right? And you want to actually get the area of these things to be as big as possible, because what they represent is along these edges, this represents loading from memory, and inside here represents computation. So the bigger you can make the area, the more computation you've done for each thing you've loaded. So the square is the best one. But then you get these ones on the edge where, because of the shape, you can only make a triangle or you can only make a pentagon. And you don't know what you're going to get passed as an input when you start doing this. So you have to then make all of the ones that could happen. So you say, okay, let's say the degree went down a little by 1. What would it look like? You do it again. And eventually what will happen is you can see that these triangles keep getting smaller, and then eventually they vanish. And now you're back to shapes you already saw before. So this is by construction, that these are the only ways the tile transitions can occur. And this is also another big part of optimization of you need case distinctions. You get a huge gain in most problems out of having good case distinctions that let you behave differently for different regions of the input. But you also need to be able to actually write code for them. So it's important that you kind of constrain them and say, I have enough case distinctions that I get a gain, but not so many that I can't implement it. So we didn't say anything about how big to make those tiles. And so the first thing to try would be cache tiling, where you say the tile size is based on the cache capacity. And there's two things about caches. So one is how many elements you can actually put in them. But then there are some constraints on which memory locations are allowed to go in which cache slots. And that's called associativity. So it can, depending on your input, it can effectively limit the size. So that's what you've got to try and tile with. And the cache is there to prevent you from doing memory operations. So what you're trying to do is put things into cache once and then reuse it a lot. So the other nice thing about the cache tiling is that the hardware is going to prefetch for you with the cache tiles. So when you start loading memory addresses on an x86, it doesn't actually load one address at a time into the cache. It takes what's called an entire cache line from where it's loading and loads it as a unit into the cache. And you can't get out of that. That's how the hardware works. So if you want to optimize something, you ought to cooperate with it and try and make it that when you load a single value, you actually want all the values that come after it that are on the same cache line. So this is the first thing we tried. And this is a standard thing to try. So if you're going to tile, the first thing you do is you cache tile. And so the question is, did we get any speed up out of it? And at this point, we were a couple of months in of having gotten the math worked out to the point that we could do this and the implementation for it. And so then we were all depressed because our speed up was basically 0. And so at this point, we have to stop and ask ourselves, did we do something wrong? Did we just completely misunderstand the problem? And so how about, did we at least reduce the number of cache operations, our stated original goal for why we were tiling? So chips have on them what are called hardware performance counters. And they tell you what the chip's doing. And you're able to peek in and look at them while things are running. So they tell you things like how many instructions have been executed. They tell you how many cache misses there were. They typically will tell you things like how many TLB misses. And there are libraries that let you read those. So the most common one for Linux x86 is called PAPI. And for Solaris, it's called CPC, is the library that you use for those. So we just went along and we instrumented our code. We put in a couple calls to these libraries and said, show us how many cache misses there were in the untiled version. Show us how many there were in the one we tiled. So there were less cache misses. So we got something right. It wasn't a complete failure. And do we give up? Or do we have any ideas? So what do we measure next? And actually, maybe a comment about measuring. So the other big part of any performance tuning is measuring, because you need the case distinctions to get the speed, but you need the benchmarks to see that it actually worked and you picked the right case distinctions. So what about register tiles? So we'll tile for the next smaller part of the hierarchy. And maybe what our problem was is that there's not enough compute per word for cache tiles to help. So even though we've done less memory loads, maybe we can't do enough arithmetic on the number or on the ones we've loaded to actually see much of a speed up. So this is another chance to not stall the CPU. And if you notice, what we're trying to get by doing all of this is the same thing that GMP had by hand. So IPC is instructions per cycle, and we're trying to get the peak for that, because what that's saying is if you get the maximum IPC, it means that you've retired as many instructions per cycle as the processor is capable of. And so now then we've saturated it the same way that they did. So, all right, we try register tiles, and do we get any kind of speed up for that? And first, maybe a little note about what the register tiles look like. So this is a square tile that we had from before, and I'm only going to show squares because the other ones are basically all the same except they've cut off some portion of this edge. So the first thing that happens is we have to load all the data in, and so we call that the register load pass. And inside of each pass, there's a number. The number is the order that we're scheduling them in the code we wrote. So we tell it to load this one, this one, this one, this one. And we next do a computation pass. And so you still need a couple inputs at the beginning, so you have to do a load in both of these. But when these loads finish, when this is done and this is done, you can now compute this value. And so we compute it first. And if you'll notice, we then go to this one second, and then this one third, and we continue down in this pattern of the fourth, the fifth, the sixth, the seventh. So we have this little zigzag down, and then eventually we get to the end, and we're still doing a little bit of computation, but we now have to store the answers. And there's a reason we made this too wide. And the reason is not that we think that there are 2 units in the CPU that are able to do the arithmetic. The reason is that we're generating C++ code, and we want to expose the dependency pattern in a way that the compiler can schedule. And by spitting out all of this code and generating them in a pass that's too wide, what happens is the compiler can see the dependencies, and now it can schedule whatever it wants because it knows how many execution units are actually inside it. And there's been a bit of a motivation for this. So you could argue this is not optimal, and in fact that we know that there are more than 2 integer execution units in every single CPU we looked at. So why did we do this? And the reason is shelf life of the optimization. So if you're going to spend 18 months doing something like this, you don't then want to say, the next CPU that comes out, I'll spend another 18 months doing it. You want to have some ability to say, when the next CPU comes out, I'll just rerun what I had the first time, and it'll figure the new answer out. And part of that is letting the compiler do the scheduling. So it's a bit of our portability. And we probably could have done a little bit better if we had scheduled it all ourselves, but then we would have lost that portability. And so you can see the pattern just keeps going. So we do this tile, like we do this pass here, and then we just keep doing 2 wide passes until we're done. So a bigger tile would just be more 2 wide passes until everything was finished. So what does that look like in terms of code? So I didn't show it to you because it's about 40,000 lines of code, and it wouldn't fit on a slide very well. So we had about 1,000 lines of Perl as a code generator, and our input is the edge size. So this is how many inputs go in along one edge of the square. And you can see, so we start with 4, you don't get very much code, it keeps going up. So one of the people that I was doing this with joked that we really shouldn't actually call it C++, we should call it assembly, that happened to be in C++ syntax. And the reason is because it was super specific. So basically it was load this memory address, load this next memory address, add these 2 registers together over and over again. And the other thing is the amount of code, it's a little bit hard to see because there's a high startup cost. The amount of code being emitted is cubic in the size of this, and so it just keeps going up as it gets bigger. I would also argue you couldn't do this by hand. I think I'd be personally incapable of writing all this code and not getting it wrong. It's incredibly tedious. It's really easy to get wrong. And this is just to generate the code for one of those triangles for the 2 sub-algorithms. So there's another 40-some thousand lines of code for the other one that we're testing, so which is where you get to the 4 lines of code turned into more than 80,000 lines of code. So we're running on this, and there's some question of, are we going to get any speed up? And so this is a while ago that we did this. These were more or less current CPUs when we did it, so we tried it on all 4 of these. And they're all a little bit different, right? So this one's a 32-bit one, and we did that because we wanted an older one in that was sort of representative of previous generation CPUs. And then all of these are 64-bit, so this is sort of modern what you'd have now. They all have very different numbers of registers. So this one only has 8 general purpose ones, this has 32, and these both have 16. And for the Pentium ones, this is maybe, you might say, a little bit unfair, because this is the number of visible programmer registers. There's all the rename registers that it's using behind the hood to let you have more parallelism than would be obviously available. This is how many integer execution units there are. So these are the things that are adding. So this is how many you can do at one time. these together determine the optimal size for the tile. And so of the different tile sizes, these are the optimal amounts. I still haven't said whether or not there's actually a speed up for this, just that this tile size was better. And you can see there's not really any obvious relationship, right? You might say, oh, there's some obvious patterns that I'd expect of something like this one has more registers, so it should have a really big tile, but that's not true. It's an 8x8 tile. Despite the fact this one has half as many registers, it's bigger. And one of the things that it also points out is it's not easy to figure out what the right answer is for this. I don't think if you went and said, so first of all, it's not all published. The chip manufacturer is not going to tell you everything that's in it and how it works. And secondly, it's pretty complicated. Even if you had a bunch of Intel engineers and you said to them, I'm going to run this on it, what's it going to do? I don't actually think they would know the answer off the top of their head, or maybe even be able to figure it out. So now here's some speed up. So here is the degree of the polynomial. So this is basically as the input is getting larger. And this speed up here is computing that Taylor shift compared to a GMP implementation. So the answer is the register tiles actually made a pretty big difference. We're getting things like a factor of 7 speed up. And what's happening here is these are the different tile sizes. So you can actually see there's a really big variation. So a question I sometimes get is, why did you stop at 16? Why didn't you try and generate bigger? And you can see when you're looking, so this guy right here, the red, is clearly much better than most of all the other ones and is the highest performing one. And it's 12 by 12. And what's happening is, so you might say, well, oh, if 12 is good, maybe 14 is better, because the bigger the tile is, the more of a savings you get on memory operations for loading. So where's 14? 14 is all the way down here. It turns out it's one of the worst performing tile sizes, and 16 is even worse. So what's happened here is we've hit a competing phenomena called register spill, where when you try and use more registers than the machine actually has, the compiler, as it's going through and sees you using all of these variables, says, okay, I've put as many in registers as I can, and now you ask me for more, so I need to make a place to put it. And the way it makes a place to put it is it says, let's pick a register that has something that you put in it, store it to memory, put something in the new register, and then when you're done, I'll get rid of what you just put in, and I'll load the other thing back from memory and put it in the register again. So there's diminishing returns, and it becomes counterproductive to get larger. So we were able to say, okay, we've searched across a number of tiles. And the other thing is you can see this is getting rapidly worse, right? So going to 14 drops you all the way back here. 16 gets you here. I suppose we could have kept going just to keep showing it sort of flatten down, but it's not going to get better. Like, we know why they're worse. There's no expectation that making it, say, 32 is going to somehow help. The other thing is you can see there's a lot of these, and you have to test them. So what we're doing for ranking them is we just say, okay, we generated all the code for this, we ran one of them, and now let's just look at the area under this curve. And if there's more area, it was faster in general, so we like that one better. And that's the general procedure for how we picked everything. That also takes about 6 hours to run on CPU to get the answer. So you can see why maybe people wouldn't be thrilled if the compiler did this for them every time they compiled the 3-line loop, that it said, okay, hold on, let me go take a break for 6 hours and decide how to schedule all of this. But if you do it once when you install the software at the beginning and then all your computations are faster, maybe it's worth the speed up. Another thing that people tend to ask when they see this is, what's all this over here, right? Everything looks so great up here, and we've got a pretty good speed up, and then all of a sudden it falls apart. That is tons of cache misses. And we did not figure out exactly what's happening. There's something, GMP has the same problem that we have at this size, and all of these little spikes down are basically cache misses going up. We kind of speculated in some of the papers that it was the associativity, but we didn't actually know. It was more hand-waving. So here's now the same thing that we had before, but it's on all 4 CPUs. And so you can see that some of them are kind of similar. You're getting decent speed ups on this one. This is another 64-bit CPU that has a large number of registers. This is the one we were looking at before, and this is another one where it's pretty good. And over here, not so great. We don't want to be on this side, right? We're slower than what we're trying to beat. So being over here, not much of an accomplishment. We had a decent expectation that that was going to happen. And there's two reasons. One is we were utilizing the fact that 64-bit arithmetic made the problem easier, and there's only 32-bit there, so that's one handicap for us. But another one is there's not very many registers. And so you can see what's happening is, so blue's 6 by 6. So here's the guy that won. He got some speed up, but it's much smaller, and the spill effects are starting to kick in at 8. And so by the time you get up to these larger tiles, it hurts you a lot. And one thing I didn't mention is the reduction in memory operations scales as the tile size divided by 2. So you actually get a big gain for increasing the tile size and how much memory you reduced. So now, that was, so before we were comparing ourselves to the assembly implementation, same algorithm in both cases, so that's just raw speedup. So now what we're going to do is we're going to take the tiled method that we had, and we're going to do the same thing, and we're going to say, here's increasing input, and here's speedup. But now, what we're comparing ourselves against is one of those asymptotically faster algorithms. I think we're using a cubic algorithm that's tiled, and they're using an n log n algorithm. And you can see for small inputs that we're doing much better than they are. And so now, this is only the best tile size for all of them, and now it's just different CPUs for the color. And you can see, okay, we're in pretty good shape here. And eventually, the complexity is going to catch up with us, and we're going to get back to, we're at parity with them for speed. But so there's something to think about for parity. So we're at parity for polynomials of degree 10,000. So you have to ask yourself, when's the last time you wanted the roots of a polynomial of degree 10,000? Can I have a show of hands? Yeah, so every time I give this talk, no one raises their hand. No one cares. They don't have problems that are that big. And so if you had to pick between over here where people normally are, where we're much faster, and this complicated one that is better for problems we don't have, we'll stick to the easier one. So another thing that people ask about this a lot is, what are these spikes? They kind of look like they're every power of 2. And they are every power of 2. And the reason is that the asymptotically faster one is doing something a little bit off in buffer management, and it's rounding up to the nearest power of 2 when it doesn't need to. And so it's basically generating itself a whole bunch of extra work that it didn't need here, and eventually it kind of decays off down to the bottom because now it actually needed all the memory that it allocated. And then it goes back to allocating too much memory and continues down. And you might say, well, oh, that's not fair. Someone could just do a better job of going back and implementing that, and it wouldn't be like that. But it's one of those complicated algorithms, and it's not clear that it really is that someone could just go back and fix it. It might actually be that the algorithm was hard enough to implement that that's kind of as good as it gets, and you don't have a lot of room in there to optimize. So complexity can kind of get you, and if you come up with a super complicated algorithm, you're going to have a hard time manifesting it in code that actually works well. So now we can go on and start measuring so what we were looking at before is the cost of processing those nodes in that recursion tree. So now we're going to look at actually processing the entire recursion tree. And there's two major costs in there. There's the tile evaluations, which is more or less the number of nodes, but also has a little bit to do with how big the numbers are for the coefficients. And then there's the depth of the tree. So obviously, every node has to be processed. If you have lots of nodes, you're going to do a lot more work than if you have fewer nodes. So it doesn't really matter what these are in terms of math. The point is we're trying to be fair in what we're benchmarking. And so we're doing some random polynomials because they tend to have very small trees. They're not very deep, and they don't have very many nodes that have roots in them. So, and they're also kind of representative of, I guess you could say, average. These we're doing because they have very wide trees. So what happens is a lot of times it has to bisect the node and take both sides of it. So this is going to give us relatively wide trees. And maybe a quick note about some of the people that we're competing against in this. They're using math tricks to try and make things better. So one thing that they've done for these is if most of these you can go through and say, I'll take the square root of x and lower the degree by a factor of 2. And the algorithm that they're working on is, I think, cubic in the degree. So that's actually a big savings. It's like a factor of 8 that they're wiping out. But they're basically doing it by a special case. So it's heuristic, and sometimes it works, and sometimes it doesn't do anything. So to make it so that you can't see that as sort of an unfair bias, we just go and do it all ourselves and reduce them and feed them inputs that will do the same thing they will. And that's not actually unfair, because if we wanted to, we could do the same thing they did and take the square root. But then it's a special case optimization, not a general one. And we picked another one. So these polynomials generate very, very deep trees. And it also points out an implementation issue. So for one of the packages we're comparing against, the deep trees actually overflowed the stack, because what it was doing was it just kept recursively going down, and it wasn't possible to actually continue evaluation. So okay, what do we get for all of it? So we have the same thing of now we have increasing problem size, and you'll notice we're going to a much smaller degree now, and we have speed up. So the reference now is not assembly. The reference is a traditional implementation in software that uses the Taylor shift, which was the triangle on this side. So that, the first thing we do is we switch to the other triangle, where you're going and getting two outputs at the same time, because you do a third of those, and they're roughly the same cost. That's this speed up. So you basically got about what you were expecting of, it's about 3 times faster, you did about a third as much work, okay. But the next thing that happens is, so now this is us tiling the one where you do a third as much work. And so if you remember from those previous slides, it was about a factor of 8 faster, and this is about a factor of 3. And so we get almost the perfect product of the speed up for both optimizations. That's really important when you're optimizing things. Your goal is to find optimizations where it multiplies through, where you get a gain in one and you can multiply it by a gain in the other one. You don't care if you pick up 10% in one, and then when you do the next one, you pick up 10% and that's it. You got the 10%. But if you get even 10% in one and then you get a factor of 10 in another one that multiplies by that 10%, now this is how people that say things like, oh, I'm 1,000 times faster than this other thing, this is why. They found stuff that multiplies through for the gains. And then these are some people we're competing with, and they did worse than us, which is sort of the main point of the slide. And there's more where they did worse than us for pretty much all of them. So here's a couple more. So here's random polynomials. Here's all the methods. So this is, again, this is the base software implementation. Oh, one thing I left out. So these ones that we're beating that did worse than us for basically all of the inputs, they all use GMP. And they're using it to be able to have the optimized arithmetic, because they thought that, oh, that would be much quicker. And you can see it kind of varies. So, okay, as would be expected, I showed the one that we did the best on the previous slide. And if you look at the other ones, we did well, but not quite as well. But the pattern pretty much continues of, you get a decent speed up, you get even better tiled. They're in between both of these. It also shows there's a lot of different ways to attack the problem. And some of them are algorithmic, some of them are pure systems implementations, and what you're really trying to do is get them to line up so that you can pull as many of them in at one time as you possibly can. And then this is also, you might say, why are there only 3 up here? The reason is this is the one that they have the sort of synthetic advantage of taking the square root, so we didn't count them here. And this is them over here, which when they can't take the square root, we're doing better. It's worth about a factor of 8. You can maybe argue we should have plotted it because they would have been about the same as us, but they're not really running on the same input. And this is, line is missing, but it's for a different reason. This is the one that stack overflowed, and it stack overflowed at an input size of about 80, and the graph starts at 100. So there's no data for it. So if you're curious about any of the math or more of what we did exactly, these are 2 papers that came out of it. And we have a few minutes if anyone has any questions. And I've been requested to get the microphone before people start asking. So if there's no questions, everyone can enjoy the end of the conference. Thank you all for coming out.